All right, so if you happen to skip the last video, we're talking about Dijkstra's algorithm here, and the two important things you need to know before you begin this are graphs and priority queues with a binary heap, both of which I have a lot of content on in this course. So what is the algorithm? It's one of the most famous and widely used algorithms around. Pretty much every computer science class around the world learns it at some point. And more than that, it's not just an academic thing. It's not just an interview challenge, although it often is, or it does come up in interviews. Most importantly, it's used all the time. Often, big tech companies will base a lot of their more proprietary, sort of special secret algorithms on top of Dijkstra's, add in some of their own special flavor, I guess. So we'll talk about what that would look like and a lot of the use cases. But what it does primarily is it finds the shortest path between two vertices on a graph. So if we have a graph with 10,000 different vertices, how do we get from point A to point B? What's the fastest way? There could be a billion options on a really large graph. How do we calculate the shortest one? So that's the problem that Dijkstra's algorithm solves, hence the term or the name Dijkstra's shortest path algorithm. First, let's talk about who Dijkstra was, just a sidebar here. So Edsger Dijkstra, I'm butchering it, I know. He was a Dutch programmer. He actually died relatively recently. Well, not that recently, but 2002 or 2003, I believe. But he was working in the early 20th century when computer science was sort of a new field. And he was a bit of a polymath. I think he started as a physicist, theoretical physicist. He wrote a bunch of essays, not to mention tons and tons of academic papers on programming, mathematics, problem solving. Really smart guy. And more than just smart, very influential. So he helped to advance the field of computer science from, at the time, was more of a burgeoning art to the crazy academic discipline that it is now. He really established a lot of the academic rigor that's present in computer science. He came up with a bunch of papers, most of which are still cited today. I read some fact that out of the 30 most influential papers, he wrote 6 of them, I think. Something like that. I don't know how you determine most influential, but anyway. The other thing is that he actually created new fields within computer science. Single papers that he wrote spawned off these new disciplines. So very, very influential. And unlike some other pioneers whose work sort of at the time was very important and led the way for other breakthroughs, a lot of the stuff that he talked about and wrote about is still in practice today or commonly used, like Dijkstra's algorithm. So here's a little screenshot from Wikipedia. On the right side of his Wikipedia page, like any sort of academic figure or really any person, there's a little bar that says known for. You can see he's known for a lot. Up top, his main achievement that people recognize today, Dijkstra's algorithm, but there are many other algorithms, as you can see, but also things like self-stabilizing distributed systems, shunting yard algorithm, smooth sort, separation of concerns, early software architecture. He did a lot and contributed a lot. So really cool guy and very, very important person. Now the algorithm itself, it is listed up top. It's widely used, widely taught, as I mentioned. And we've kind of explored the main idea behind it, finding the shortest path between one point and another. But the story of how he came up with it and why he even tackled this problem is kind of interesting. I don't know if this is 100% true, but it's on Wikipedia, which doesn't always mean much. But apparently the impetus for him actually doing this, for coming up with his shortest path algorithm, is that he wanted a problem that he could come up with to demonstrate to the general public why computers were awesome, why they were powerful. He wanted to show something that was difficult for humans to do and how easily computers could do it. So he came up with this travel problem of finding the shortest path along the massive train network in the Netherlands, figuring out the fastest or the shortest way. This is his quote. What is the shortest way to travel from Rotterdam to Groningen? I'm not Dutch, sorry about that. From any given city to given city. It's the algorithm for the shortest path. And then here's his little humble brag, which I designed in about 20 minutes. Apparently he was shopping and then over coffee and he was tired. He designed it at like a little cafe table in 20 minutes. And eventually that algorithm became, to my great amazement, one of the cornerstones of my fame. So it's kind of fascinating. He didn't set out to solve this as his thesis or as his greatest achievement, this problem that haunted him his entire life. It was more of I want to just come up with something that the public will understand, something that will demonstrate the intrinsic value, the worthiness of computers. How about finding the shortest path using the rail network in the Netherlands? And then that is actually what went on to have a lot of implications and use cases to this day. So lastly, let's talk about why that is. Why is it still useful? So the most obvious thing that I've already mentioned this as an example, GPS, or any sort of mapping software, whatever app you use, whether it's Google Maps, Apple Maps, whatever other versions there are out there, or you have one of those old school GPS devices in your car, MapQuest, all of that involves finding the shortest path from one point to another. And all of that data can be represented using a graph. Now, of course, there's a lot of other complications in today's world, and like Google Maps, its algorithm takes not only the distance, but the capacity of a road, the number of lanes, the traffic, accidents, weather, time of day. I'm sure there's many other factors I'm not even thinking about. Holidays. Yeah, there's a lot that goes into it, but it's still based on finding the shortest path. Now, what makes something short might be different, because our version we're going to talk about, we're looking at a single criteria, like distance on a map. We're not implementing traffic and all of that stuff. But at its core, we could take Dijkstra's algorithm as we're going to learn it, and then tweak it to add in traffic or to account for weather and that sort of thing. Next up, network routing, finding the shortest path for data across a massive network. If you think of computers, they're connected in a graph. Let's just say 1 million computers. How do we break up a large message into a bunch of little pieces, send it across a bunch of computers, and end up at another computer? What's the fastest, shortest way to get there? Biology, it's used often to model sort of the spread of infectious diseases across humans, often used in projections. I have no expertise in that. That's just something I read online, but I found fascinating. Airline tickets. If you ever go on those websites and you enter where you're trying to go from one city to another, let's just say one way. Of course, you can optimize for all sorts of different things like duration, price, number of airline miles. But if you're willing, let's say you're trying to come up with the cheapest possible option and you're willing to make like 3 different stops. Well, there's a lot of options and it would be a huge pain to try and manually compute that. But using a shortest path algorithm where it's optimizing for cheapest rather than shortest distance, you might end up flying across the world a couple times, but it might be cheap and you might have long layovers, but the algorithm could do that, could figure that out for you. It looks like I put biology on here twice. Whoops, sorry about that. And many, many other uses, as we'll talk about as we go. But we're going to start with just a bland old graph. Maybe look something like this, where we have numbers representing the distances between cities or junctions in different paths. But before we can even talk about the algorithm, we have one small problem, which is we don't have a way of storing this data right now. If we simplify it, get rid of that map background, we can't do this part right here. We don't have a way of storing the information about a given edge. Our graphs are just vertices and edges. They are undirected, meaning there's no arrows. They are both ways. But they're also unweighted, meaning there's no value associated with them. So the first thing we need to do before we can find a shortest path, we need to just add distances or add a weight to our graph. So it's not hard. It will just take a minute or two in the next video. That's what we do next. So then we can actually implement a shortest path algorithm. So in the next video, I'll be back to write a weighted graph.